Hello, dear students. I welcome you again in this series of lectures on modern physics, which we also call as engineering physics. And in our previous lecture, we talked about vectors and their properties under rotation of coordinate system. Today, we'll focus on the coordinate system itself. And what is a coordinate system, why it is important, and what kinds of coordinate systems are there that we very often use to solve the problems of physics, motion, and electrodynamics. So this lecture will be all around the different kinds of coordinate systems, and then there are plenty of coordinate systems. Because there are many symmetries, mathematical symmetries that we can use to solve a problem. For example, we have Cartesian coordinate system, spherical polar coordinate system, cylindrical coordinate system. They utilize the plane, the cylindrical, and the spherical symmetry of a problem. But we can also have ellipsoidal coordinate system, a parabolic or a paraboloid coordinate system, depending on whether you are talking in 2 dimensions or 3 dimensions. You can have an elliptical coordinate system and so on. So since at undergrad level we mostly deal with the problems that have either spherical symmetry or cylindrical symmetry or Cartesian symmetry, then only 3 of these coordinate systems are important for us, and we will discuss only these 3 coordinate systems. First of all, why we use different coordinate systems? That is the very interesting question. We use different coordinate systems because it depends on what problem we are addressing. If there's a problem that has some symmetry, we can use the symmetry of the problem because that makes the mathematical equations much simpler to address, to solve. For example, I have a line charge and I want to calculate its electric field. It turns out that if I use the cylindrical coordinate system and use cylindrical symmetry, then the equations that I deal in figuring out what the field is become much simpler. So a body moving on a circle, for example. So if I use polar coordinates, then it is very simple to address this problem rather than addressing it in Cartesian coordinates, because these Cartesian coordinates would mix up in a very complicated way. So the fundamental idea of using different coordinates is this: to pick up a coordinate system according to the problem. The problem will tell us which symmetry it has, and accordingly we'll select a coordinate system to address that problem. And why do we choose a particular coordinate system? Because that very coordinate system makes the problem mathematically elegant and simple to address. So let's get started. So first of all, why do we need a coordinate system? So what is the need for a coordinate system? Because unless you don't have a coordinate system, the location is meaningless. So if you want to locate a particle or a point, or you want to find electric field at a particular point in space-time, then you need to tell me where that point is. So for that, you need a reference frame, or you need a reference setting. So coordinate system is nothing but it's kind of a reference framework, and which is used to locate a particle, and then the particle can have motion. It will change its coordinates, and accordingly it will update these coordinates. That will tell us a lot about what it is doing, whether it is moving with constant velocities, accelerating, and blah blah blah. Similarly, for example, I have a charge. I want to find electric field at some point. Where is that point? What do we mean by at some point? Unless you don't have a reference frame, unless you don't have a reference background, that point becomes meaningless. I mean, you need to understand how far you are from that charge, and it is very important to set a background reference standard which will tell us where we are. So that is why we need a coordinate system. Let us begin with a very simple 2-dimensional coordinate system and locate a point in this 2-dimensional coordinate system, and then trace a position vector and express this position vector in terms of its coordinate labels. So let us do that. So what I do is that very simple setting. Let us do it. What we do is take a 2-dimensional setting, a 2-dimensional frame or reference system. Yeah, so this is our 2-dimensional reference system. So, and there is point P in this system. I have a point P, right? And I label it by two coordinates x and y because this is my x coordinate and that is my y coordinate. And in the x direction, I have a unit vector ex. In y direction, I have a unit vector ey. So one way of labeling the point is that how far it is from x-axis and how far it is from y-axis, and that is what x and y mean. X means that how much we have to go along x, and how would we reach this point P? I will go x distance along x, and then I will travel y distance, and y displacement I will reach to the point. So the other way of locating, so this is a Cartesian way of locating it, okay? Let me draw a position vector now. So that will tell me where I am. So let's draw a position vector. So, okay, this is my position vector. And let's call this position vector as R vector. And it is oriented, its orientation with respect to the x-axis is given by angle theta, right? Another way of labeling P would be that I will say that how much it is distant from the origin, that is the magnitude of R vector, and how much it is oriented, so that is the orientation here is given by the label theta. So that is called polar representation. So we represent in coordinates r and theta. We can represent the same point with coordinates x and y. X and y are the Cartesian coordinates, and r and theta are the plane polar coordinates. Okay. Now, how would I express this r in terms of x and y? So the r vector is x ex, right? And then y ey, right? Very simple. The way you express a vector in terms of its components, right? And I can also say that, you know, x is in terms of cos, I can write r cos theta ex plus this is r sine theta ey. Because I can look at the diagram and I can easily figure out that this x is nothing but it is the projection of this r. So this is x by r is cos theta, magnitude of r is r, x by r is cos theta, so x is r cos theta, and this fellow is y, and y by magnitude of r is sine theta, so y is r sine theta. Very simple geometry. It's mostly high school standard geometry. So what I mean here is that x is r cos theta and y is my r sine theta. So now you can see that is the relation between the two coordinates. X is expressed in terms of r and theta, and y is also expressed in terms of r and theta. Now I can write r in terms of x and y. I just square and add these two coordinates, so these two equations simply. So it's x square plus y square. What would be that? That would be r square cos square theta plus r square sine of square theta, right? So nice. So nice so far. So or x square plus y square is simply equal to r square, as cos square theta plus sine square theta is 1, or r is equal to root of x square plus y square. So this is how r is expressed in terms of x and y. So these are how we transform one coordinate in terms of the other coordinates. Like I have two representations, I have xy and r theta representing the same point. I can express r in terms of xy, so I can transform Cartesian coordinates to polar coordinates, and I can also express theta in terms of xy. How would I do that? I just have to divide these two equations, divide this equation with this equation, and what do you get? So let's see. So then you get y by x, I write, and that you can see is simply r sine theta is y, and x is r cos theta, and this fellow will go. So tan theta would be equal to y by x, and that means my theta is nothing but tan inverse y by x. So these are called the transformations and the inverse transformation. So you can see that I can write, can see here that x in terms of r theta, y in terms of r theta, r in terms of xy, and theta in terms of xy. So I can go from one coordinate system to another coordinate system. So both the coordinates represent the same point, but there are two ways of labeling these points. One is that I can choose Cartesian labels x and y, or I can choose these polar labels as polar coordinate labels as r and theta. Good one. Now there are certain things to note here, interesting things to note here, is that you see that x and y both have the dimensions of length. They are both length coordinates. But r is a length coordinate, theta is no dimension, so the labels need not have same dimension. So the coordinates that we choose to locate a particle need not have the dimensions of length only. They can have dimensions, anything. Their dimensions could be anything, right? But here in this simple setting, the r has the dimensions of length, but theta is dimensionless. So there is no constraint on that. There is no requirement that the coordinates should have the dimensions of length. Another thing is that in case of Cartesian coordinates, my unit vectors are ex and ey. Now the question is, what are the unit vectors in polar coordinates? What would be the unit vectors in polar coordinates? Now you see that is my direction of r, right? In the direction of r, I choose a unit vector er. Fine. And in the direction of theta, so I say theta rotates like this. The orientation goes like that. So normal to r is e theta. So there are two vectors, e theta giving the direction of theta and er giving the direction of r. So for r, the associated unit vector is er, and for theta, the associated vector is e theta. So that means er would be in that direction, right? And e theta would be in that direction, right? But er and e theta would also be normal to each other. So that means in this case, my er is in this direction, can write that, and my e theta is in that direction, and you can see they are normal to each other. But as I move from point to point, say it is at this point, I'm showing the direction here at this point. But if I go to a different point, different location, say my point P is, say here, point P prime you call it, right? Now I draw a position vector here at point P. With point to point P prime, I draw a position vector. Let us suppose that is the position vector. Now we can see that your ER is in this direction and your E theta is normal to that, but that is not the direction of this ER and E theta. That is different. So at every point, the direction of ER and E theta changes, but EX and EY will maintain the same direction. Doesn't matter where you choose the point, right? That is a very important takeaway, that the unit vectors in Cartesian coordinates keep their direction. Doesn't matter where you are in the coordinate system. But in case of polar coordinates, at every point you will have a different direction of ER and E theta, but they will remain perpendicular to each other. So that's a very important takeaway, and this flavor is preserved in other coordinate settings. So let's see how I can express E theta and ER in terms of EX and EY. So let's do that. Now, what was my R vector, right? In polar coordinates, it was r cos theta, right? And then it was Ex plus r sine theta and Ey. Basically is X plus Ey. X is r cos theta and Y is r sine theta. Now ER, by definition, ER, that is the definition of a unit vector, is that you find how position vector changes in that direction with respect to how position vector changes with respect to that coordinate divided by the magnitude of this particular quantity and this particular element, right? So what you need to find is that you will, in order to find any unit vector, say any unit vector, what I will do is that I will differentiate the position vector with respect to that coordinate and divide by the magnitude. So in that case, if I differentiate it with respect to r, so this ER, what would be ER? ER would be, now I differentiate partially this equation. I differentiate this equation partially with respect to r. So now theta is constant. So this is 1. This is 1. So I will have only this term because EX is constant, EY is constant. So I will have cos theta EX and sin theta EY. That's what will remain because differentiation of r with respect to r is 1. All right. So what remains is now, when I differentiate, what do I get is cos theta EX plus sin theta EY. And now that is what I get in the numerator. Okay, but in denominator, if I find the magnitude of that, so that is my, actually let me write it down. That is my dr by dr. That's what I get. And if I find magnitude of that, dr by dr magnitude, that is cos square theta, that's root of cos square theta plus sin square theta. And that is 1. So therefore, ER would just be this dr by dr, position vector, derivative of position vector with respect to r by unity. So that would be cos theta EX plus sin theta EY. Very nice. Now, what would be E theta? So we want to find E theta. How would we find E theta? Yes. So again, I write what is R? Yes, what is R? R is R cos theta. Yes. EX plus R sin theta EY. Now I want to find what? E theta I want. What will I do? I will differentiate R with respect to theta and then divide by magnitude of that particular. All right. Let us do first just what we do is we differentiate R with respect to theta. Now R remains constant, theta is differentiated, so minus R sine of theta EX plus R cos theta EY. That's what you get. And then magnitude of that, if I find magnitude of del R by del R, right, that would be root of, this will be R square is common, sine square theta plus cos square theta, and that would simply be R. So I have to divide with the R to get E theta. Therefore, E theta is equal to minus sine theta EX plus cos theta EY. So now I have found position vectors ER and E theta in terms of EX and EY. So let me write now both the vectors. So we have ER. What was ER? It was cos theta EX plus sin theta EY. What is now E theta? It's minus sin theta EX plus cos theta EY. Now from these two equations, you can easily see that ER dot ER, just take dot product of R with itself. You can do that exercise, very simple. So you will see that's equal to 1. And you can also think of, because you know EX dot EX is 1, EX dot EY is 1, but EX dot EY is 0. Use that idea, you will get this thing. Similarly, E theta dot E theta you can also prove to be equal to 1. and you can prove that er dot e theta is equal to 0. So these are very interesting products that you can calculate. You can prove that they are orthonormal. These, like we have ex, ex and ey are normal to each other. So are er and e theta. At every point, the direction may change, but at every point they are normal to each other. Fine. And how do I write a length element, a small length element in this coordinate setting, right? In this framework. So in Cartesian coordinates, dr is simply ex dx plus ey and dy, and the same can be written in polar coordinates as dr. In polar coordinates would be er, sorry, it would be er dr, that's fine. And we expect like e theta e theta d theta, but something is missing here. What is missing here is this is length element, that's fine. Unit vectors don't have dimensions. This is length, dimensions of length, dr has dimensions of length. It's anyway a vector, right? Because you are multiplying with unit vector here. But this is dimensionless, and unit vectors don't have dimensions, so I can't add this quantity to the length. So something is missing here. So I want to find what is the length in the direction of theta. So how would I find that? Now see, you see this is your r, that's your r, right? And say this is your theta, and this length is nothing but r d theta. So that length is in which direction? That is in the theta direction, and dr is in dr direction, this length, right? So instead of just e theta d theta, there has to be r d theta if it has to make any sense, because that's what it is. So it means that it's like dr is equal to, we can write it like e dr, it is d, it's like e r dr plus, now it is e theta, this is r d theta. One has to be careful while writing the line elements, line segments in different coordinates. So the line segments, there will be two line segments. One line segment along the r, other line segment is normal to that r, and these line segments are any vector can be written in terms of these line segments, and they are r dr and r d theta. That's how you write it. And we call this as a scale factor also. We'll talk about it later. So this is how you express a length element in polar coordinates. So we have seen how to express unit vectors in polar coordinates. We have seen the relation between the coordinate, two sets of coordinates, and how they transform into each other. Now we will go into 3 dimensions, and we'll talk about a very important coordinate system, which we call as cylindrical coordinate system. And it will teach us a lot, right? And we'll start with Cartesian coordinate system, 3-dimensional Cartesian coordinate system, go over to cylindrical coordinate system, and then of course we'll talk about the spherical polar coordinate system. Fine. Okay, so let's do that. So let's first of all define a coordinate setting, a 3-dimensional coordinate system. Okay, so let's do the cylindrical coordinates and introduce you with the cylindrical coordinate system. So the point P has labels like x, y, and z in Cartesian coordinate system, because there are Cartesian coordinates x, y, and z. And in the cylindrical coordinates, what you do, you have this vector rho, right? Just like your polar coordinate rho, and then x would be rho cos theta, and y would be rho sin theta, because this angle is 90 minus theta. So you fix x and y with this length rho, right, on this plane x and y, and then you keep z as it is. So because this rho has circular symmetry, it is r theta, it's r and theta, rho and theta, that is circular, and then you have this height also, so you have a circle and height that will give you the cylinder. So that is the it has a cylindrical symmetry, this kind of coordinate system, where I choose rho, I choose theta, and I choose z as my coordinates. So these are called cylindrical coordinates. So another way of labeling the same point is, so rho, theta, and z. Rho is like r we had in polar coordinates. Now we label it rho because r is reserved for the position vector. So now let us see what are the position vectors. In this direction, the position vector is e rho, fine, and normal to that in the direction of theta, it is e theta, and then in the z direction, it is the same ez. So that would be the three position vectors. Now let's write down the r vector, right? There will be three unit vectors, not position vectors. There are three unit vectors. Okay. So now write down r vector. So in both the coordinate systems. So the first thing I will write it in Cartesian coordinate system. It would be x, ex, right? The way you know how to write it. Y, ey, and then z, ez. Fine, nice. Now let me write the same in cylindrical coordinates. Now what are my cylindrical coordinates? X is rho cos theta. My y is rho sine theta. And my z is z, because I keep the z as it is. So one of them is Cartesian only. I'm only taking polar coordinates and mixing it with the z-axis, and z I keep as the same kind of coordinate system which I had earlier, same kind of coordinate that which I had in the Cartesian form. So that's what the cylindrical coordinate is. So in cylindrical coordinate, only the x and y become rho and theta, the z remains the same, because that's what the cylindrical symmetry is all about. It is circle, which is rho and theta, and the y-axis that makes a cylinder. All right. And then I can put it there. So I can write r is, for x I write rho cos theta ex, right? Plus, yes, y is rho sine theta ey, and then I write z ez. Same thing, nothing different there. Fine. And now this is what it is. Fine, brilliant. I would like to define my unit vectors. What is e rho? How would you get e rho? You will have to differentiate r with respect to rho, and then divide with the magnitude, right? And when we do that, what do we have? We differentiate with respect to rho. There is rho here, right? There is rho here, so this will remain. It will differentiate, that is 1, this will remain. There is no rho, this will be 0, right? So I will get what I got earlier also. So I will get rho will not be there. It will be now cos theta ex plus sine theta ey. Fine. That third component would not be there because there is no rho in there. And magnitude is 1 anyway, because that is root of cos square theta plus sine square theta. So the divided by the magnitude of del r by del rho is anyway 1. So that would be my e rho. It is the same thing as I found earlier. So e theta would again be the same thing which you found earlier, that is minus sine theta ex plus cos theta y. And ez remains what it is. So you can verify all those dot products again. So you can verify that e rho dot e rho is equal to e theta dot e theta is equal to e phi dot e phi is 1. So this you can take up as an exercise and do it. I will be very happy if you do it yourself. Now I want to write down the length elements. So I think that what we have, it's a very simple setting. We have polar coordinates plus z-axis. So it should be very easy to write down the length element, right? So let us do that. So what we have now, we have dr we want. So what would be that in Cartesian setting, in Cartesian axis coordinate system? It would be ex dx, come on, it would be ey dy plus ez dz. Fine. And what it will be in cylindrical coordinates, that would be Cartesian coordinates. What would be that? The same thing in cylindrical coordinates. It would be e rho. D rho. Remember, d rho has the dimensions of length. So no, rho is like your r. The earlier, which was r, is now rho, because now we have r, a three-dimensional entity. So we have the two-dimensional r is your rho, right? Plus, and now this will be e theta d theta, but the proper is e theta r d theta, and then e phi. And no, what was that? Ez and dz, that remains the same. It's nothing but it's our original polar coordinate plus one dimension is the same. So that's how you write dr. I can write this as like, this is the length element dl some rho, right? This is length element dl rho e rho, plus this is dl theta, length element dl theta is r d theta. So e theta plus this is dlz. dz is dlz, length element in the z direction. And then that is ez. This is another way of saying the same thing. Because now I want to define the area elements. So let us now define area elements in this setting. What are the area elements? We need to define now area elements in this setting. So how would we define that, right? How would we define area of small areas? Very important. See, area plays very extremely important role in physics problems, and because we are not only concerned with the surface but the orientation of surface. So it's not the surface that's important, it's also important how the surface is oriented. So there are two things associated with the area. One is the surface itself, which is the magnitude, and the orientation of surface will define. We have to define some direction sense to the area, and only then I can say that this area is oriented this way, that way. You see, when you calculate flux, how do you calculate flux? You need to define an area through which the field will pass. You also need to define how this area is oriented. Fine. And another important idea is that when you can use the vector idea, you can use the concept of vector. You can represent a vector by a geometrical object. How do you represent a vector by a geometrical object? What is the representation? You take a line with an arrow. So that represents a line with an arrow is your geometrical representation of a vector. So what is the geometrical representation of a vector? That's simple. It is length. Simply you take a length, you define some length with an arrow. The magnitude of the vector is defined by the length of the line, and the arrow defines the direction. Now, suppose I want to see that how would I write area in terms of the when I map vectors, right? How would area map to the vector algebra? That I have to check. Now, for that reason, I take a kind of, say, I take a very simple geometric figure, say a rectangle, right? Now suppose this is my L vector and that is my B vector, and I want to define area. Now anyway, area is the product of length and breadth. Now there's only two ways I can map this product with the area. Either I take length dot breadth, that should give me area, Or the other possible product is length cross breadth. That should give me, right? So I check with this one, right? If I find that, you can see that the angle between them is 90. So L dot B will map to 0, but the magnitude of the area for the Euclidean area for this rectangle is not 0. So the dot product doesn't give me the right answer for the magnitude of the area. And another problem with the dot product is that it doesn't specify the orientation of the surface. So now if I check with the cross product, so that would be LB sine theta is 90. So it's L cross B, L cross B is magnitude of L, magnitude of B, and the sine of angle, that is 90 degree. And N vector, which is normal to both. This is how do you define cross product. Normal to both L and B. Now this is one, so this is simply length into breadth and a vector. Length into breadth is the Euclidean area we know, that is the area as a number, and N gives me the orientation of the surface. So not only I specify the magnitude of the area, but I also tell you what its orientation is, because that is physically very important, that in case you find out the divergence of the field and in so many other things, and where you need this concept of orientation is very orientation, we will need to map this vector area as a vector element, right? Area as a vector. So area would qualify as a vector because vector has two properties. It is magnitude and direction, and in that sense it is the area qualifies as vector. But remember that there is one problem with the area, that it would be a pseudo vector, because if it is a cross product. Any cross product of two vectors qualifies as a pseudo vector. It would be the problem is if I rotate it, transformations would be a bit complicated. So keep that in mind. And what about volume? How would volume be defined if I take length, breadth, and height as three vectors? How would I get volume? So you will get volume typically like you have, if you take a cube and define its length by one vector, breadth by another vector, and height by another vector. Now when you take area of the base, that would be a vector parallel to the height vector. And only if you take a dot product, then it will make sense. The cross product will not make sense. So that means L cross B cross H will not be a volume, but like L cross B dot H, this would qualify as volume because volume has no orientation. So that maps very well. So what are the different area elements? How do we write these area elements, right? So starting with say Cartesian coordinates, you will have three length vectors. dlx is the length element with ex, that would be the vector in that direction. Then you have another length element is dly. It's like dx dy, right? So that is ey. Instead of dlx, you can write this as good as dx, right? And this as good as dy. I'm just generalizing in terms of length. And then you have dlz is something like a dz. This is ez. That is the length element or length vector. So I want to find area daxy. So this area vector. This area vector means that if this is x-axis and this is y-axis, then any area element here is axy. Direction of that would be in the z direction, because axy is like dlx. This is dlx and this is dly. So this is the cross product between dlx and dly, and that would be in the direction of dz. So how do I write daxy? How do I write that vector? I write it as dlx ex cross dly ey. So that would be dlx dly ex cross ey. That is dlx dly, and that is Ez. So the area vector is normal to the area itself. This is the area itself, right? So, and normally the convention is that you take this area vector, the unit vector, outward, always outwards to, that's the convention, that the area vector is always normal to the surface and pointing outward. So it's always pointing outwards. That is the convention. You don't tell me that why not inward, but that's the convention. Once you choose one convention, we'll stick to that convention only. Now, similarly, now we can go to a different coordinate. So you'll have, we can also define a, y, z, and d, a, x, z. Similarly, you can define these things as well. Now, in case of this cylindrical coordinates, how would you define these elements, these area elements? So dA rho theta, right? So how would you define that? dl rho e rho cross dl theta e theta. Remember, dl rho is length element in rho direction, right? And dl theta is length element in theta direction. And this would be dl rho dl theta, and e rho cross e theta is Ez, right? And dl rho, I can write d rho, and dl theta is r d theta. So then you can express them in terms of the coordinates itself, right? Similarly, you can write other area elements in this coordinate setting. So far so good. So we have seen Cartesian coordinates, three-dimensional Cartesian coordinate system, and we have also seen that if there is a cylindrical symmetry, how I can write down these coordinates, how I can write down these coordinates in terms of cylindrical coordinates, or cylindrical coordinates in terms of the Cartesian coordinates. The unit vectors in the both coordinate systems are now defined, their products, the length elements, that's all done. And how to express a position vector, first in Cartesian coordinates, then in cylindrical coordinates. We have covered that. Now we will have another very important discussion, which is about spherical polar coordinates, extremely important for mechanics and electrodynamic problems. Spherical polar coordinates. Now we will have some commentary. We'll discuss spherical polar coordinates, and we'll see that how we can label a particle or a point by xyz or by r, theta, and phi. Phi is the azimuthal angle, and then we'll find the unit vectors and their representations, and also express these spherical coordinates in terms of Cartesian coordinates and reverse transformations, write down length elements, area elements, and the volume in this setting as well. So let's go on and let's do it one by one. So fine, so let's draw a diagram and explain. I'll draw a diagram on this side this time, because I think I'm eclipsing some important ideas. On this side, I'm also actually learning how to make better use of iPad and other things. Now this point is P, and that is my position vector, and this fine. So this is our position vector. This is my x coordinate, and then ex is the unit vector in that direction. That's my y coordinate. Ey is the unit vector in that direction. That's my z coordinate, and Ez is the unit vector in that direction. Fine. Assume this angle with respect to the z-axis is theta, right? And theta gives me the orientation of r with respect to z-axis, right? So theta gives the orientation of this this position vector with respect to z-axis. Now what I do is that, you see, this is a plane, right? And this is at some angle with the z-axis, and with respect to this plane, this angle, this is theta. The total angle with plane is 90 degree. So this angle would be 90 minus theta. So what I do is that I drop it as shadow, right? If you take some torch here and see it as shadow, that's called a projection. So the projection of R on this plane, what would be that? So that's what we will write. So the projection of R on this plane would be, so that is the projection, right? And since that is theta, this angle is theta, this angle is 90 minus theta. And this is r cos theta, and this will be r sin theta. So therefore, I will write this is r sin theta. And this r sin theta has an orientation, say, with respect to x-axis, phi angle. So therefore, along this axis, so now you see this is r sin theta. What is its projection on the x-axis? Is r sin theta cos phi. So I can write this now as r, x is now r sine of theta cos phi. And what would be its projection on y-axis? It's r sine theta. This is cos phi. You see, this is cos phi. This angle is 90 minus phi. Now, therefore, it would be r sine theta cos of 90 minus phi. The projection of this on this, that is sine phi. So therefore, I say y will be equal to, come on, r sine theta sine. And what about z? The projection of r on z is simply, this is theta, so it's r cos theta. So that means z would be equal to r cos theta. Now the point can be labeled as x, y, z. The same point in spherical coordinates is r theta and phi. The theta is the angle with the z-axis. Phi is the angle that the projection of r makes with x-axis. I think the idea is very clear. Now I want to write down this r vector in terms of x, y, z. There are two ways of doing it. Right, I can write now r vector, right, is equal to x plus y plus z. And what is x? Come on, x we have found is r sine theta cos phi. What is y? It is r sine theta sine phi. And what is z? It is r cos theta. So now you can see that x can be expressed in terms of r theta and phi. Y can be expressed in terms of r theta and phi. Z is also expressed in terms of r and theta. Now I can have reverse transformations, scaring and adding. You can just scare and add. You will find x square, you'll find x square plus y square plus z square. That is equal to this sine square will be common. This is cos square plus sine square is 1. Then sine square plus cos square is 1. Simply is r square. So r in terms of x, y, z is x square plus y square plus. So simple. Now, if I divide these two, y and x, so let us do that also. Y by x. So sine theta and sine theta will go, r and r will go, you will have tan phi only. So that will give me phi in terms of tan inverse y by x. So nice. So now phi is in terms of y and x. And what about theta? That I can do simply. I can divide. You can just write down theta in terms of z and r you can write root of x square plus y square plus z square. So you can write cos of theta as z divided by root of x square plus y square plus z square, and theta would be the cos inverse of that factor. So now you have expressed x, y, z in terms of r theta phi and r theta phi r theta phi in terms of x, y, z. So you can transform cylindrical coordinate, these spherical coordinates into Cartesian coordinates. You can transform Cartesian coordinates into spherical coordinates through these transformation equations. Now we'll go back and now analyze. These were transformation equations. We'll now analyze back. We can go back and analyze this position vector thing. Okay. So what is now your position vector R in spherical coordinates? Axis R cos theta. No, what was that? R sine theta. So it is R sine theta is cos phi plus R cos theta sine phi. Of course, this will be Ex. This is Ey plus R is cos theta E phi Ez. Sorry, Ez. Now I want to find Er. Right, so that you have to find as del R by del R and divide by magnitude of del R by del. Find with respect to R, so it is sine theta, because when you differentiate with respect to R, that R differentiation is 1, so you remain sine theta, and cos phi will remain with Ex plus cos theta sine phi Ey plus cos theta Ez. So nice. And magnitude, divide by the magnitude, you take sum of the squares, that you will see is 1, because sine square and cos square is, you can just see that is equal to 1. So something is wrong there. Sine theta cos phi, this has to be sine theta sine phi. Yeah, so something is wrong here. Something is wrong there. I could easily figure out that something is wrong there. This has to be sine theta and sine phi. So sine theta, sine phi. Now the magnitude would be 1. Because your sine square theta is common here, cos square plus phi plus sine square phi is 1, and then sine square theta plus cos square theta is 1. So you just divide by 1. Right. Now similarly you can find E theta. So you have to differentiate R with respect to theta and divide by the magnitude of that vector. So that fellow would be equal to, now differentiate with respect to theta, sine theta is cos theta. There's R cos theta cos phi Ex. Then come on, for sine theta again cos theta, R cos theta sine phi y plus R cos theta z. And the magnitude, you can see that cos square would be out, then there would be cos square theta would be sine square plus cos square is 1, then we will have we'll get R. I mean, I think we should get R. Not made any mistake. Sine theta was cos theta, sine theta was also there. That was cos theta. Oh, there is this thing. Okay. Yeah, so here it is sine theta. Cos theta is different, minus sine theta. This is minus sine theta. That was something wrong. That's why magnitude was not coming R. Now it will come R. So because this is cos square theta will be out. Sine square plus cos square is 1. This is sine square plus cos square. That's 1. So you have to divide with R. The magnitude would be R. So then you will have E theta is equal to cos theta cos phi Ex plus cos theta sine phi Ey minus sine of theta. Similarly, you find E phi, and then you prove all those things, and that Er dot R is 1, and you prove that Er dot E theta is 0. You can also prove their cross products. Er cross E theta is some E phi. You prove those all orthonormal relations for these unit vectors in r, theta, and phi direction. So now we'll talk about how to represent the length vectors. Okay, lengths. So that's we'll go to the original setting, original coordinate system. Now this is anyway, sorry. So this anyway is your DLR. That's fine. That is your DR anyway. So DLR, a length element in that direction. What about a length element in this direction? Right? This is theta. This is d theta. So this will be this length element in the direction of theta would be r d theta. No problem. And this is phi, but this r is r sine theta. So this length element would be r sine theta d phi. So you have three length elements. One is that dr as it is, dr. The second is rd theta. The third element, this element, length element normal to this fellow in the direction of d phi, in the direction of e phi, that is r sine theta is the radius, and this angle is phi. So this angle is d phi, and therefore this is r sine theta d phi. So now I write down the three length elements. So dl, the dlr, right? Write down this vector that would be equal to dr er. Fine. What about dl theta? That would be r d theta e theta. What would be dl phi now? Come on. That would be r sine theta and d phi phi. Now you can find all area elements, like you find dAr theta. What is that? That is dLr cross dl theta. What is dLr? That is dREr cross r d theta e theta. And what is that? ER cross E theta is E phi. So it is R dr d theta phi. Similarly, you can find dA theta phi. This vector, that would be dl theta dl phi. And that would be, sorry, these are vectors. So that would be, yes, dl theta is r d theta theta dot, sorry, cross product. Anyway, cross product. What is dl phi? So it is r sine theta d phi e phi, right? So this would be r square sine theta d theta d phi e theta e phi is er, right? Because normal to both theta and phi is er. Similarly, you can find, so how, if you want to find volume element, so come on, let's find volume element here, dV. That would be simply the product of these three, because the unit vectors will multiply to get 1. So it will be dLr, dl theta, and dl phi. What is dLr? Is dr, rd theta, and this is r sine theta d phi. And that would be r square sine of theta dr d theta d phi. This is volume element in a spherical coordinate system. So I think we are done today. So we have we started with the polar coordinates, Cartesian coordinates in 2 dimensions. So we started with the 2-dimensional coordinate system, 2-dimensional coordinate system. Then we talked about Cartesian and polar coordinates. We talked about polar coordinates. These would be important for problems with circular symmetry. Then we discussed unit vectors, length elements in these coordinates, how to define unit vectors in polar coordinates. And most of the physics was, most of the mathematics was already done here. And then the cylindrical and spherical coordinates, it is the repetition of all the ideas that we learned in 2 dimensions. Then we talked about cylindrical coordinate system. We found the unit this position vector in terms of the cylindrical coordinates, and then also we found different length elements, different area elements. Similarly, volume element can be easily written as a product of all the length elements. So we found unit vectors and we proved the unit vector identities, like how they multiply their dot product and cross product. That can be worked out. And then finally we talked about spherical polar coordinates, very important, polar coordinates. And we expressed spherical polar coordinates in terms of the Cartesian coordinates. These are the transformations and the reverse transformations we also discussed. We expressed position vector in terms of x, y, z, and in terms of r, theta, phi. Then we found the unit vectors of the spherical polar coordinates in terms of the unit vectors of Cartesian coordinates and proved their orthonormality. Then we found, then we also expressed the different length elements in spherical polar coordinates, the area elements in spherical polar coordinates, and finally also the volume element in spherical polar coordinates. So I think we have covered all the important coordinate frames, which are very important to do physics problems in this module. And all kinds of questions that we will take up will require only these coordinate systems. And there are other coordinate systems for other problems having those kinds of symmetry. But normally at undergrad level, or the problems that we encounter, we restrict our discussion to these three coordinate systems. So now where are we after two lectures? In the first lecture, we introduced the concept of vector. We introduced the concept of the rotation of a vector. Then we introduced it in the second lecture. We introduced it different coordinate systems and how one can go from one coordinate system to another coordinate system, and how we can generalize these coordinate ideas, coordinate systems. We can also generalize them as what are famously called as curvilinear coordinate systems that we have not yet touched. Now, in my next lecture, I will be talking about fields and how fields are represented by mathematical functions, and then how we involve vector calculus to find interesting features of these fields. We're talking about gradient, divergence, and curl of the fields. And once we set up this whole mathematical scheme, then we will talk about electrostatics, Maxwell's. Then you can understand Maxwell's equations and the applications of Maxwell's equations, and that would help us to cover this module very effectively. So I think after two lectures where we have covered some portion of vector analysis, and then we have covered different coordinate systems and how one coordinate system is related with another coordinate system. Do a lot of practice. I will be also discussing some problems with you. So then take care and see you in the next lecture.